Okay, so here we have another problem, and this is actually a problem from an FRQ from I think 2004. So here we have this problem, and very similar or very common problem that we see in this type of chapter, where we have a roller coaster, and we are thinking about conservation of energy of this roller coaster. So we have a roller coaster ride at an amusement park, lifts a car with a mass of 700 kilograms apart to point A, so right up there at the very top of the peak. At the height of 90 meters above the lowest point on the track, and we'll call the lowest point 0 so that we have everything from there. Um, the car starts from rest at point A. So at point A, there is no velocity. And rolls with negligible friction, so we don't have to worry about non-conservative forces, down the incline and follows the track along a loop of 20 meters. Point B is the highest point of the loop. It has a height of 50 meters above the lowest point in the track. So the first thing that we want to do is we want to indicate on the figure the point P at which the maximum speed of the car is obtained. So what we want to think about is, for this problem, let's go ahead and say part A. What we want to remember is that if all of my potential energy, my gravitational potential energy, is turned into kinetic energy, this happens at the lowest point. So where is the lowest point on my diagram? Well, the lowest point is going to be right here. So right here is point P, and that's where my speed is going to be the greatest. And so now my problem says, okay, well, what is that max velocity? What is that speed? And so we actually just identified what is happening. We have all that potential energy at point A being converted directly into kinetic energy down there at point P. So if I were to plug in this information, I have M, G, H, and I'm going to go say HA so that we know that we're talking about point A is equal to 1/2 mv, and we'll say point P. Actually, let's do max because the problem does say what is the velocity max squared. The mass of our object does not change, so we can cancel out mass, and we're going to solve for our velocity final. So we know that the gravitational potential energy is 9.8 meters per second squared times our height at point A, which is 90 meters, is equal to 1/2 V max squared. What we end up getting is that our velocity max is equal to 42 meters per second. And so that is our max velocity, and that of course occurs at point P. Now the problem says, calculate the magnitude of all individual forces acting on the car when it is upside down at point P. At point B. So what we need to think about, let's draw a quick diagram and think about what that car looks like at that point. So let's say that we have part of our loop. So here's our loop. Let's kind of zoom in. Here's just like half our loop, and here is our car. Now, what forces are acting on that? Well, we have two. We have our first normal, because remember, our normal force is always perpendicular to our force of contact. And of course, in the exact same direction, we have our force due to gravity. Now, both of these forces together, the sum of these forces is equal to our centripetal force. So we've talked about this idea of our centripetal force. So let's think about what that would look like. So let's think about our equations. We know that the sum of all of the forces, which is our centripetal force, and actually let me just erase that. Let's just put Fc is equal to mass times my acceleration of centripetal acceleration, Now let's think about what our force C is. So our force C is going to be our force normal plus our force due to gravity which is going to equal our mass times my centripetal acceleration. And my centripetal acceleration is v squared over r. Okay, so let's think about what we know. Now, we don't really know anything about our normal force yet. We can't derive anything. We can calculate our force due to gravity. So our force due to gravity, if we think about that, Fg, I'm just going to put this off to the side. Fg is going to be mass times our gravity. So that is going to be, our car is how many? 700 kilograms times 9.8. So if we plug that in, what we actually end up getting is 6,860 newtons. So there's one of our forces. So that actually takes care of one, but we want to know our force normal too. Okay, so we know this value, we know this mass, we know the radius, but what we don't know is our velocity. Well, if we think about this problem in the same way that we thought about it in part B, we can actually calculate our velocity at that point. So let's think about it this way. We know our velocity right here at point P. So what if we say that point P is our initial and B is our final? So let's look at that problem. So again, we need to think about what is the velocity at point B. That's what we need to plug in here. So if we say, let's see, 1/2 mvi squared. So this would be at point, this is P. You could have also used point A and use our potential energy. I'm going to go ahead and just use this one. Now at point B, we have two forces, so it's still moving. So we still have 1/2 mv final squared, and we have mgh. We have our gravitational potential energy. We can cancel out our masses. We know our initial velocity because we already solved for that. What we are trying to find is our velocity final right here. So let's go ahead and plug things in. We have 1/2 42 meters per second squared is equal to 1/2 v final squared plus 9.8 meters per second squared times our height of that loop, which is 50 meters. What we end up getting for our v final is 28 meters per second. Okay, now that was kind of a lot of work just to get that value, but we did need that value. So we need to solve for our force normal. So if I were to plug this in, I'm going to go ahead and let's just divide this. I don't want to make it too confusing, but we have our force normal is equal to mv squared divided by r minus fg. So if we plug in what we know about this, this is going to be equal to the mass of the car. It's going to be 28 meters per second, and this is all going to be squared, divided by our radius, which is 20 meters, minus our 6,860 newtons. Okay, so we have those values. Go and scroll up. Now we can plug this into our equation, and we can get our force normal is equal to 20,000. Ooh, got a little off there. This is 20 meters. So our force normal is equal to 20,580 newtons. And so those are our two forces acting on it. Last problem, it says, in order to stop the car at point B, some friction must be introduced. So again, stopping the car maybe at point B would be the top. Some friction must be introduced. We need to calculate the work that must be done by the frictional force in order to stop the car. So again, thinking about that work force. So we have our non-conservative force. So we have MEI. I'm just thinking back to that one problem that we did. Force due to friction, work due to friction is equal to ME final. So again, this initial mechanical energy, this could be at point A or point B. So this could be point A or B, just like it could have been point A or point B in the previous one. Let's go ahead and stick to point B just because we have that already. Our work due to friction, and then our mechanical energy. And again, our mechanical energy is going to be mgh. But if we want this to stop, that means that we're going to have no kinetic energy. So our kinetic energy is going to be 0 because we want it to stop, which means that we want to have no kinetic energy. So let's go ahead and write this out. So we're going to have, let's say, point B. So we're going to have 1/2 mv, we'll say initial squared, plus our work due to friction, which is really what we're trying to find out, is equal to mgh. Let's plug in our values. It's going to be 1/2 700 kilograms times our velocity squared, which we said was 42 meters per second squared, plus our work due to friction, which is equal to 700 kilograms times our gravitational times our height, which is 50 meters. And if we rearrange that equation and we think about what our work, and we solve for that, we get our work due to friction is equal to a negative 274,400 joules. You could also say negative 274.4 kilojoules, either one, but that is the work that would be needed to be done by friction in order to stop the car.